My name is Amalaye Oyake. I work for the Jet Propulsion Lab. I work for an instrument science data section. And for the past, I would say, about the past 10 years, been working with a group of people at JPL on networking things in space, or simulated things that are supposed to be in space. And the title of my talk is The Internet of Space. It's a play on the popular term Internet of Things. So I'm going to get into this a little bit. So I'm going to be introducing and mentioning a lot of people along the way and citing lots of material. So there will be a lot of material in this presentation that it was created by other people. So you'll see some of that. So a bit about me: I work in an instrument group, but many years ago I used to work in a software infusion group. And the purpose of that group, the group was led by Abdullah Al-Jabri, and there was a project at JPL called Deep Space One. Some people may know of it, where they flew Lisp on board a spacecraft. It happened. It's never happened again. But it was really a cool mission. But the leftover hardware from that mission, the single board computers, basically RAD 750s and a bunch of other things, all lived in Iraq. And the group I was in, which was the infusion group, their job was to basically take new sort of application layer, high-level software and try to infuse this into a flight software architecture. So, so some of the people, Scott Burley. Scott, you can wave your hand. So Scott Burley is a flight software programmer, DTN architect, I said, for NASA. There are a few other people, but as far as I know, Scott's the person I work with, and is the NASA lead for ION DTN in terms of software development, and works for the Interplanetary Network Directorate. That's a very cool sounding name, and I think that's led by Jay Wyatt. Jay's over there. A few other notable people. I just want to say hello to Larry Bergman, who's sitting in the audience. So I work for Larry as well. Lots of cool people. But a lot of the work sort of started with some of these people. And I at the time was working in this software infusion group. There is another lab at JPL. It's called the Protocol Technology Lab. We also call it the Protocol Test Lab. That's led by Lee Torgerson. And he is mainly one of the key CCSDS points of contacts at JPL in terms of testing lots of these protocols and those sorts of things. So we do, every year we do lots of very interesting protocol tests between JPL and also with other NASA centers. So I shared a little bit about myself. So as part of my work for this infusion group that I was a part of, Scott worked in something called the Flight System Testbed. Basically, it was a lab in the corner of the spacecraft assembly area. And people were doing tests all the time and with their flight hardware, and they needed to do message passing between the flight computer and the ground GDS systems, which were at the time mostly SunSpark systems and maybe some other things. But Scott had written a publish and subscribe software called Trammell at the time. I remember it because I did use it, and that was the thing that people used. And so, but the world of DTN was sort of being created and sort of message passing and things like that. And the task I had, it was many years ago, it's been so long ago, was to port Scott's work, which lived on these workstations, into VxWorks and see what happened. And so that was sort of the beginning of sort of a long journey of this. And so I did the first VxWorks port, and then I did a port on an RTEMS port of ION, and worked with some other interesting people. I worked with a person by the name of Takahiro Yamada on something called the Spacecraft Monitor and Control Protocol, which was a monitor and control protocol. It's kind of a RESTful API for spacecraft instruments and devices. So we got to sort of the CCSDS draft level. It was more or less, rejected, saying, missions aren't going to do this because missions do their own thing. But the interesting thing is JAXA took this and just has pretty much gone crazy with it. They use this, they basically matured this protocol within their organization. And I got an email from Takahiro, we use this on all our missions. So, okay, that's interesting. And then, so when I see sort of RESTful APIs and things like that, it reminds me of some of our work on that. But so what is IoT? The general ideas. You see IoT everywhere, the terminology, and so what the feeling you generally get is that IoT is the next big thing. I mean, companies are spinning up, hiring people. You have whole marketing departments. Everybody's doing something on this IoT stuff. But you hear certain claims. If you want to do Internet of Things, if you want to connect your toaster to the internet, you better have a persistent and reliable internet connection. Something with a network address, you need TCP, UDP, JavaScript, HTTP, and something cool sounding. That's, some nice, something like Node.js or some other, you just whip out something cool sounding to make somebody feel inferior. But, that's generally the feel. We've got this cool language, it's being able, we can communicate with all these different things. And devices can be networked using web protocols, or there's some other protocols. And you can even purchase very powerful IoT frameworks to enable smart devices. So you can go to certain companies that I will not mention and buy their IoT frameworks and network all this stuff and do lots of cool things. And you can spend a lot of money doing that. But and I have this line here. It says, ignore everything listed above. So that's all cool, but part of the premise of this presentation is that a lot of the IoT ideas and claims, while they are very exciting, are not entirely new or original, and you actually may not need very much to network device A to device B. And the interesting thing is that you might even, the thing that you're talking to may not even be a device. It may not have power. You may not even be able to talk to it. It might just have an RFID patch on it, and that's it, maybe with a temperature sensor, something like that. So you may not need much to talk to something that you're trying to observe. But a good thing to note is that there are many standards bodies that actually deal with networking and communication and all these sorts of things. And so ITU, CCITT, CCSDS, OMG, IETF, DTNRG, OSF, ISO, and our ham radio friends. Anybody here have a ham radio license? Okay, good. A few. All right. So, like I said, while IoT is presented as something new, the ideas are not really new. So people have been networking things for a long time. Might sound silly, but with sound, fire, smoke, sun, electrical signals, and telegraphs. So some examples, there's a very excellent book. I think it's out of print, but if you're doing anything IoT related, I strongly encourage you to get this book, wherever you can find it. It's hard to find. I have 2 copies, I don't lend them out, so. One is the one I read, and the one is the one I hide away in case I lose the one I read. So some of the examples of networking are Alexander the Great's 12-foot megaphone, Claude Chappie's semaphore system, basically a messaging system with these arms. You kind of did like this, you could get a whole alphabet. CM's electric telegraph concept, 1753, Jihu's telephone system, 1796, the Swedish telegraph system in 1796 with a data rate of half a bit per second. You can actually go to Sweden, and I think some of these still exist, actually. Cook and Wheatstone's electric telegraph, 1837. And many of these systems were actually used for networking train signals. So if a train's going into a tunnel and other ones are going into a station, you could say, okay, train number 1, go ahead. Train number 2, stop. Train number 3, just wait till everybody gets out of the way. And what they discovered, if you read this book, it's really interesting, is that uh, there were protocols for how these vehicles, trains, interacted, how they went through tunnels and came out of tunnels. And what they found was that the protocols were oftentimes, incompletely specified. So you had an incident like the Clayton Tunnel train crash, where one train went in, another train went in too fast before the signal could be sent that, oh, there's a train actually in the tunnel. Third train came along, didn't see the signal, and you had a major accident. So some networks that existed over, I would say, the past 40 years, some of the are Aloha, Autodin, Arpanet, Satnet, Autodin2, Sabre, which is used in the airline industry, and many others. And if you read publications by some of these organizations, UCLA, University of Hawaii, and lots of other places, you'll find a lot of documentation on their efforts in networking. So here's a picture of the book. I just wanted to add this. So this is the book, and on the cover you can see the Chappie semaphore system that was used. So that made up a full alphabet, I believe, of uppercase and lowercase characters A through Z. And so if you ever stumble across this book, do get it. Definitely recommend it. So some other historical notes that I also wanted to point out. These are really interesting papers, and when you read them, you really start to see that the ideas of networking things, particularly electronic devices and having some kind of intelligence, were being looked at by lots of people. So one really interesting paper is on distributed communication networks from the RAND Corporation by Paul Baran. Another really interesting memo was the memorandum for the members of the affiliates of the Intergalactic Computer Network. Really interesting paper. If you can find it, it's easily downloadable, read it, really interesting. Vinsurf's store and forward packet switching, discussed in packet communication technology protocols and techniques for data communication networks in '81. And a lot of the stuff that came out of Smalltalk. And I actually got this from there's a famous conference in Australia. It's called the YOW conference, and one of the speakers was Gregor Hoppe, and I saw this. I said, this is and then I talked to Scott Burley about it, and this is really interesting. He said the big idea with Smalltalk was not objects, but was messaging and passing messages, and it was something that was never quite completed during their time at Xerox PARC. So I found this really interesting, that the idea of objects or devices sort of existing, a big part of it was just them being able to pass meaningful messages between one another. So a few pictures from some of those talks. So this is the all-digital network, Paul Baran's diagram. And so in the picture you'll see actually a heterogeneous network of television stations that function as network devices, also buried cables, and also a satellite link on the far right. And so you have this network that's composed of a mixture of links. And so I found this picture from 1964. Some references say 1962. I found it really interesting. Another is from Licklider's paper, and these are some of the graphics that are in his paper. It says, what is a node? And and this is from 1968. He says, an operating system, graphical display, interpreter, user program. Sounds like Unix. This is 1960 something. So found it really interesting. All nodes can be connected, can be interconnected via their message processor. So they came up with a concept of interface message processors, or IMPs. And so when they created the Arpanet, and this is a BBN diagram. There's a really interesting article that came out not too long ago that captured a bunch of the historical Arpanet diagrams, and I cited that here. But this is one of the diagrams, the 1971 picture of the Arpanet. So you have the interface message processors, a bunch of PDP machines, and the networks that exist. So you had UCLA, UCSB, Stanford, and then looks like Case Western University, Carnegie Mellon, and a few others. By 1973, there was a satellite link between University of Hawaii and Ames, and lots of other little nodes somewhere in different places. But the network had grown, and so they were building up this network. The very interesting thing is, there's a book by Franklin Kuo, F.F. Kuo, where they basically discuss networks that are bridged using satellite links. And so they have this concept of a satellite interface message processor. So instead of your typical interface message processor, you now have a satellite that is now a message passing device. And so they demonstrated this, and he has an interesting book too that's also out of print, very hard to find, where he discusses their research on this, where they have a satellite link in various regions and nodes. And this particular picture really reminded me of the DTN implementations and just the network architectures. I found it very interesting. So all of these things are things that were done in the 70s and the 60s. So we can see that people were trying to network things, at least pass packets, message passing, switching, things like that. So I'm saying that, none of this is new. So what is new? So the newness is the easy availability of small, low-cost, using the ARPA terminology, interface message processors, IMPs, or small compute nodes, Arduinos, Raspberry Pis, Beagle boards, all kinds of very cheap computers. There's a very cool one called a Red Pitaya. It has an FPGA with an ARM. It can do lots of cool things, has an A to D converter. I have one of those playing around with it. It's really nice. And also the easy availability of lots of cool enabling software, all the cool sounding software that I mentioned before. But the danger is that in trying to perform scientific experiments, do interesting things, everything sort of becomes a nail. Okay, I have a problem, how do I do it? I just download Node.js, get my Raspberry Pi, send a web message, convert that to, receive that on the node, convert it to a GPIO signal, raise the pin to high, and voila, I've turned something on. And so it really sometimes boils down to just grabbing a bunch of stuff and sort of slapping it together and making it work. And what I'm encouraging is really going back to first principles and understanding why people were interested in networking in the first place, and what were the problems that people trying to form networks were trying to overcome, and some of the problems they did overcome. And looking at your domain, if it's a simple tabletop experiment, stuff like this, you can get away with stuff like this. But if you're trying to build networks for critical systems, you should really try to understand the environment that those systems operate in, so that when things go wrong, you'll have a full understanding of the problems that are arising, or at least you'll actually see something new. So we want to do Internet of Space. It sounds cool. How do we do this? Can we form a TCP/IP link with Spacecraft? What are some of the things that are involved? So for us, what happened is, as we started to look into this, Scott and Jay started having discussions with Vint-Cerf and looking at the different concepts, and there were lots of discussions. So, well, what about this? How about this? And Vint would say, well, you don't want to try this particular solution because we've proven that this solution is suboptimal, or we tried that before, it didn't really work very well. And we got a lot of good guidance and direction. So he basically provided a lot of insight and guidance into a lot of what we were trying to do. So as you look at communication in space, we're looking at communication that's very disrupted, lots of delay. The communication can be intermittent. A spacecraft can move behind a planet. You can have occultation by various things, very long one-way light times, all kinds of things. And so what we use is disruption-tolerant networking, which is a framework that has been created out of lots of discussions that looks at the environment that we are trying to communicate in. So we're trying to communicate in space. It's not an internet where you have sort of millisecond delays or those kinds of things. We have lots of other problems. And so we look at the environment and some of the challenges that exist in that environment. And the DTN protocol has been formulated with an understanding of those constraints. And so it's an approach to network architecture that seeks to address the technical difficulties in those environments. So things like remote sensors in Antarctica, spacecraft in deep space, the submersible vessel. So in DTN, you have asynchronous variable length messages called bundles, which are routed in a store and forward manner between participating nodes over a heterogeneous network. So that kind of sounds familiar. So if you go back, sounds something like store and forward packet switching and intergalactic kind of stuff. So these are some of the ideas. Again, sort of not new. People have looked at these sorts of things. Implementations include ION, which I use, DTN2, which was discussed earlier by ISRO, BPRI, don't know a lot about that, and DASM. So the key is to understand the requirements and capabilities of the underlying infrastructure and environment and basically take advantage of it. Okay, so I talked a little bit about this. So DTN is an architecture. It's not a protocol, but a suite of protocols. And it has various features that are built into the standard or described by the standard: security, network management. It is supported by standards bodies, IETF and CCSDS. There's a working group. There was a slide here, but let's see. Oh, there we go. So internetworking layer that functions efficiently in environments with time disjoint or simplex links. A reliable data link layer that improves efficiency of end-to-end delivery by leveraging the local link information and tighter local control loops. And disruption-tolerant routing services that can take advantage of scheduled and expected future connectivity in addition to current connectivity and interoperate with or without terrestrial routing infrastructure. So quality of service mechanisms as well. And improved operations and situational awareness. So you have this store and forward mechanism along with automatic retransmission that provides sort of more insight into events during communication outages and reduces the need for ground-based scheduling. So the one thing is when you have this store and forward mechanism, when you have this capability that automatically provided, you have less of the situation where you're manually going to command the spacecraft to retransmit your data back to you. This is handled by the protocol. Space link efficiency, I think Bill Van Biesen talked a little bit about his trade study, and that got a lot into this, basically using as much of the link as you can. And talked a little bit about some of these things. So So the ION implementation is specifically designed for resource-constrained environments, embedded systems, so our spacecraft and embedded systems. So you can use it. It's specifically designed in terms of flight software design rules, memory management, and those sorts of things. So it's an implementation specifically tailored for space-based vehicles. ION development began in the early 2000s. There's a date here of June 2003. I tend to believe it started much earlier than that, but it started in the early 2000s. That's what I can remember. The first use of ION in space was the Deep Impact Network experiment that happened in 2008. I was a part of that team, basically doing a lot of the image builds on our VxWorks build system. And we had a team of other people. Andre Girard, Rashid Amini, Nuhad Jawad, I believe, was also part of that. Ross Jones was the manager, gave a lot of direction, Jay Wyatt, and Scott, a few others, if I can remember, but those are some of the names that I remember. And since May 2016, ION has been an operational service. The DTN has been an operational service on the ISS. So there's actually a DTN service for any ISS payload to use. So external and internal payloads can use the DTN service, and it's fully supported. Okay, so what does ION include? ION includes the asynchronous message service, which is a publish and subscribe layer where you can pass messages. The bundle protocol, LTP, and adapters for various underlying wired or wireless buses. Okay, so bundle protocol is a store and forward protocol, provides custody-based retransmission with the ability to cope with intermittent connectivity. So the bundle protocol is sort of a higher level blob of data that you're shipping. And it provides late binding of overlay network endpoint identifiers to the underlying internet addresses. LTP is a layer lower, so the bundles are broken up into segments, LTP segments, and it's also known as the long-haul transmission protocol. It's designed to provide retransmission-based reliability over links characterized by extremely long message round-trip times or frequent interruptions. LTP is named after JCR Licklider, whom I mentioned in one of the earlier slides, and who wrote the memo of this intergalactic computer network memo. Communications in interplanetary space, as we all know, is very difficult, and LTP is specifically designed for these deep space communication links. So, okay, so let's see. So it's designed for to provide retransmission-based reliability of data transmissions over deep space links. Deep space links, as I shared earlier, have many constraints, extremely long signal propagation delays on the order of seconds, minutes, or hours, rather than milliseconds. What we, on the internet, we do a ping, we get the response, you see a couple hundred milliseconds, and that's typical. When you're dealing with space and you're trying to network things, things can take a very long time, and so you have meager bandwidth and highly asymmetrical data rates. So the two-way connections can be very different. These environmental characteristics pose many challenges for people trying to network assets in space. And so if you're thinking of, okay, how do I bridge two devices or two vehicles in space, you can immediately see that the environmental constraints pose lots and lots of challenges. And so the DTN architecture tries to overcome these challenges by taking different assumptions on the protocol design. So ION, as I said, is our implementation. It's downloadable, it's open source. You can go to SourceForge and download it and play around with it. So So we talked a little bit about some of these. So I really want to talk about some of our case studies and some of the examples. And so the first one was the Dinette Experiments, where we basically turned the epoxy spacecraft into a router. And so what was involved with that was we created a DTN library that was uploaded to the spacecraft and basically started. And that library provided basically the uplink and downlink capability to send messages back and forth. So the spacecraft acquired a node address and was addressable from computers on the ground as a networkable device. And so by infusing this library into the flight software, we were able to turn the spacecraft basically into a router. And so we were sending images and data up to the spacecraft, and it was routing it to different machines on the ground. And we had a simulated rover on Phobos that we were sending information to, and we demonstrated improved science and data return because the mission people actually started using this as well. And so there was a little press release. It says NASA has successfully tested the first deep space communications network modeled on the internet, as part of a NASA-wide team of engineers from JPL in Pasadena. Used software called DTN to transmit dozens of space images to and from a NASA science spacecraft located more than 20 million miles from Earth. So there's a video on YouTube. Vince Cerf comes on and he talks a lot about this. It's a really cool video. The second case was really interesting. We did a demonstration in the JPL Mars Yard. So if you were here for the earlier talk, they had he talked about a scenario where you had a rover and orbiter and a rover and 2 orbiters. Well, we actually did that a couple of years ago. And so we had a seismic sensor, a rover, a relay orbiter, and a science orbiter. And so the question was, if we create a flight-like network, so we had channel simulators that created real propagation delays. We injected errors by dropping frames, and we basically built a space-like network where the environment was similar to the best of our ability to sort of the space environment. And we had DTN running on all of these assets. So the sensors were running DTN. We had a real rover that was driving around, and we had 2 simulated orbiters, which basically were computers with cameras. And what we did was we would go out to the Mars Yard with a sledgehammer and whack a big metal plate, and then all the seismic sensor was basically sort of like a Phoenix lander sort of thing. It would send a message to the relay orbiter, who would then tell the rover that, oh, something happened over there. Can you go over there and take a look at it and take some pictures? And I will also send a message to the science orbiter, so when it flies over, it'll take some pictures. And so we were doing this in the Mars Yard, having lots of fun, just whacking the plate, and things start running around, and things were working. It was really awesome. It was really, really cool. And then we were in the shed. If you go to the Mars Yard, there's a shed over there, and it's really dusty, and we're all sitting there, just kind of sitting around looking out the window. And then we notice everything just starts moving around. We're like, wait, did someone hit the plate? What's happening? What happened? And then someone said, I think maybe there was an earthquake. I said, I didn't feel anything. Did you feel anything? I didn't feel anything. So we went to the Caltech website, the USGS website, go to check. Okay, what is this? Sure enough, it was a magnitude 4 earthquake. You live in California, 4.0 earthquake is nothing. You don't feel it. But there it was. It happened, and these things were responding, and we were actually quite encouraged by this, just to see that okay, you can actually network devices and robotic devices. They can actually respond and do things. So I actually have something else to say about this. So the USGS has an earthquake basically an earthquake network that they're building out. It's a wired network, from what I know of it. When I talk to the people who are doing that, they are sending messages over the internet, and so from earthquake sensors all over the place. My proposed model for something like that would be basically a wireless sort of packet messaging network, similar to ham radio, that sure could use the internet, but could also use maybe ham radio channels and things like that. Because if we do have sort of anything greater than a 7, we would want things that have battery power that can send wireless messages that users can respond to. And there are lots of ham radio people out there. And so DTN in that kind of environment I think would be kind of useful. So that's just my little pitch on that sort of thing. There are lots of other examples and lots of other work that we've done. And some of them are the onboard ISS scan testbed radio demonstrations, lots of other things. You can look at the list in my slides, but I'm going to skip down and just talk a little bit, show a little bit about the ion stack. So this is what the ion stack looks like. So you have an application. You can either use the message passing layer, or you can actually go straight down to the bundle protocol layer. You can also do file transfers and things like that. You can use CFDP, which is not pictured here. I don't think I did, but you can do those sorts of things. And so this is sort of what the stack looks like. And you can pass messages between the various layers right there. So, and this gives a quick summary of the differences between terrestrial DTN or terrestrial networks and DTN for space flight. So as we talked about the challenges of the environment. In space, we have to use sort of rad-hardened chips, and we have to use processing resources efficiently. We don't have a lot of memory, and we have to use generally, typically, we use real-time operating systems, though there's more of a movement towards Linux in space, so that's another thing. This is a very detailed core component diagram of ION. There's a lot of information here. It gives you a picture of the various things. A little bit about AMS. Some of the ideas that we were having. So what this picture is trying to show is that you can have local message passing between subsystems on board a spacecraft using sort of asynchronous messages. But AMS also provides a service called remote AMS, which leverages the DTN services, and so you can pass messages that will be encapsulated as bundles between vehicles. So you could have a space station and maybe a capsule that's docking with it or something like that. And so you can have message passing at the application layer or even at higher level. Okay. This shows a picture of the layers of communication. Lots of detail here. Not enough time to get into this. ION configuration. So I'm going to speak to this for just a few seconds. The key thing is really knowing your underlying file system implementation and the resources you have, knowing the sizes of your bundles, determining those, sizing your LTP data segments so they can fit through the link, either the Ethernet or the radio, whatever it is. And also reporting is also very good as well. So how do you infuse this technology in sort of a vehicle? I'm going to get into this. I presented this a few years ago, but I just want to talk about this again. So for Earth orbiting kinds of things, something that's orbiting a moon or a small planet, you would need some kind of software-defined radio, understanding how the radio behaves, station allocation files, various radio protocols, proximity 1, ephemeris information, where things are, some kind of DTN implementation that runs on your embedded system, and an understanding of how to deal with time. This is beyond the scope of this talk, but time presents its own challenges because you have various types of times, atomic time, UTC, GPS. There is sort of no nice API that's just to generate a time source for flight software. I mean, you have sort of POSIX, but POSIX does just enough, kind of, and then you have to sort of start to look at, okay, what have we implemented within our own framework? Time synchronization is in deep space. That's a whole nother discussion. So someone can present on that. David Mills, we can invite him. And so operational scenarios, relay operations. So you have orbiter acquisition of signal. Rover anticipates the arrival of the orbiter through some mechanism. And we already do hailing on Mars, and so you complete the hail and handshake sequence, and you start communicating. And use LTP to maximize the link as much as possible. And so this is autonomous relays using LTP. So again, looking at another picture of the stack, you can see some of the things there. You can see LTP point-to-point retransmission, and COP-P for retransmission, PROX1. Those are the sorts of things. Okay, in a simplified way, AOS, a proximity hail, data transfer, loss of signal, and in the most simple terms. I will skip all of these. But for deep space, it gets a little bit more complicated. So you're dealing with things like antenna pointing, radio configuration, station availability, communication subsystems, the underlying data, the science data, the housekeeping data. What are you trying to get down? So you have all of these different things sort of interacting with one another. So you have this package diagram, and how do you build a deep space communication network? And so these are some of the things you need to understand. And so I have a nice picture of lunar ice cube, because lunar ice cube guys are right here. They're sitting right in front, actually. So I'm actually working on infusing the DTN software into a radio. We have an X-band radio at JPL, and it's a CubeSat small form factor radio that lots of CubeSat missions are planning to use. And so how do you do this? And so the spacecraft anticipates ground station availability. Spacecraft transmits bundles using LTP. Ground station receives frames and extracts packets, segments, and reassembles bundles. This is a very simplistic diagram, but it gives you a bit of an idea. The previous slide shows you some of the layers there. Okay. Quick animation here. Let's see, I don't know how to do this. Let me try this. How do I do it? Okay, there we go. So it shows you a little bit of the communication. So data recovered with link errors and legacy telemetry, and sort of data recovered with DTN LTP reliability. So you drop packets, you drop segments. Those segments are retransmitted using the LTP layer. So how do we do this in sort of the CubeSats that are going into deep space? CubeSats like Lunar Ice Cube and other CubeSats like it. What infrastructure do we have? So good news is that DTN is being supported by the NASA DSN. So Morehead State University will become integrated into the DTN as a DTN station. As a DSN station. So DTN will be provided as a service by the DSN, and Morehead State is very active in that. And so this image is, if you want to know more about this, you can speak to Jay Wyatt. But in this picture, you can see a lunar ice cube type CubeSat that's interacting with the Morehead State antenna, and there's a communication link there. So, okay, so this talks a little bit about lunar ice cube. Its profile. This is all publicly available information. You can find this on the internet. But looking at deep space CubeSats, it would be useful to optimize the communication and do very interesting things with this. And the encouraging thing is by using this technology on vehicles like CubeSats, we're then we're forming the building blocks for doing more ambitious things, such as deep space, Mars missions or deep space habitats, and how do we form networks in space. Okay, this is, the ultimate vision is interplanetary networking, where we can network assets in space and have a collaborative science between the various vehicles in space. And this is the vision of the internet of space, and one of the things I've been working on for a long time. I can take a few questions at this time.
Questions? No? Okay, thank you.
All right, thank you.
You want to disconnect?